My name is Akbar Farahani, CEO at ETA, and my co-author is Dr. Kambiz Kevantash from CADLM, France. We are going to be talking about product design development using AI ML solution, incorporation of the accelerated concept to product design process, and also the AI ML solution to make sure we get the best efficient solution for product design development and speed up the optimization process. I'd like to acknowledge my co-authors from ETA, Devish Mittal, Shiva Kumar, Ming Zhang, and Abhishek, and obviously, Dr. Kambiz Kevantash, who's been very, very helpful in providing his resources to do this project. In this presentation, we will talk about objective and motivation of this project. We'll have a little bit of introduction about ETA and the software that we use in this research. We'll tell you a little bit about the strategy of the project and the results of this research work, and finally, a conclusion. The motivation and objective of this project is to demonstrate AI ML interface and potential usage of the prediction of the responses using AI ML without using any type of the parametric optimization. Second is showing this capability within the rigid barrier 0-degree frontal crash, and if we show that successfully, we are hoping to use that into the entire ACP process and ACP OpDesign process for the designing for the low fidelity design and high fidelity design and the all 3G optimization throughout the whole process. I'd like to talk to you a little bit about ETA, who we are, and what we do. ETA has a unique position in the providing services to auto industry. We provide an end-to-end solution. We provide engineering solution based on our in-house and in-client services for all different type of the product design and development, and also engineering softwares with ETA own software and our channel partner softwares, which basically complements our product line, be able to provide a total solution to our customers. Our engineering solution for in-house engineering basically are supporting all CAE type of the simulation from end to end of the total vehicle, and also provide on-site team and also product design development in the CAD, CAE, and also engineering solution. And with recent development with the product that we developed and also process we developed called Accelerated Concept to Product, ACP, we are able to provide a lot of services for weight reduction, cost reduction, product design development. The other part of our total solution is engineering softwares that ETA provides our own software as well as our channel partner softwares. ACP OpDesign, which is for the gateway for lightweighting, optimization, and design solution. DynaForm is a total solution for die design and die system simulation, and based on LS-DYNA. And our VPG suite is providing a safety and structural modules that can be used and interface with all the pre and post processor, enabling all the users to use LS-DYNA simulations. Also, Precis is another general pre and post processor that we have that is very popular using with LS-DYNA. And as far as our channel partners, strong partnership with ANSYS to provide LS-DYNA and LS-DYNA solutions. with Beta CAE as a partner with our ACP product and their softwares, and Catalem with our AI ML solution, and DCS is supporting us for all the different type of the manufacturing and digital mockup. Now let's talk about Catalem. I would like to have Kambiz to talk about Catalem, and then I'll continue talking about the project.
Catalem is a SME launched in 2014, mainly concentrating on application of new data science techniques, machine learning, reduced order modeling, etc., for handling, solving engineering problems which still cause problems because of their CPU costs, because of the complexity of the problem, and so on. The techniques we use are more or less known in data mining and machine learning. We have introduced some new techniques in fusion technology, also called model reduction. We employ optimization, risk and reliability techniques, but essentially those are also the problems we solve: optimization, reliability, robustness. We do develop our own application platform called ODYSSEE. ODYSSEE comprises of different modules. In particular, there is Lunar, which is more or less organized around optimization and reduced order modeling. Quasar, which is a very generic machine learning platform, and Nova, which is an optimizer.
Introduction to ACP process and OpDesign. Let's talk about what is ACP process, which is Accelerated Concept to Product Process. I'd like to show you a video clip that will tell you what is ACP process, and then what is the benefit of that.
What is the ACP process? A holistic and systematic approach that navigates and orchestrates through advanced software tools based on assumption and correction philosophy from concept to product. This includes the following enablers: an optimization system, which considers multidisciplinary loading simultaneously based on the most effective load path and combination of geometry, material grade, and gauge. A process that can reduce cost of resources by 10 to 15%, mass by 20 to 25%, and product design time by 30 to 35%, is based on assumption and correction philosophy. Integration of vehicle design process enablers. The ACP process integrates styling, design, and manufacturing processes with material choices as a gateway to vehicle lightweighting and performance improvements. Integration of ACP process enablers. An optimization-led design process, optimization system, that orchestrates through phases of product design and development. This integrated process and system evaluates various design concepts under multidisciplinary loads through topology and parametric 3G optimization. The structured design enablers for the ACP process is built in a 4-step process. Step 1, load path process. The topology optimization will create the most critical load path based on multidisciplinary loading despite material type and where material should be to resist the loading conditions. Step 2, material selection. Using the ACP process to find the required material type based on the available material portfolio to the parametric optimization process. Step 3, low fidelity 3G. To create a low fidelity design concept, after the creation of the initial geometry by ACP process tools, 3G at low fidelity design level will be optimized. Low fidelity 3G parametric optimization will change the geometry and balance between strength, stiffness, and gauge of all sections throughout the entire system. Step 4, high fidelity 3G. High fidelity 3G optimization of subsystems, substructure, or parts based on the available manufacturing process.
We'll have another short video about ACP process benefits.
ACP process benefits cost reduction with resources, product design and development time, manufacturing, tooling, and material costs. Multidisciplinary loading contributes to the following attributes: stiffness, crash safety, NVH, and durability. The design will meet the targets based on requirements, not the prediction. Product mass is reduced since non-essential components would not be designed, and all the parts are created based on the balance of 3G. Reduce product design and development time. If we look at a product's degree of maturity versus time, the following chart displays a blue curve, which represents a conventional product design cycle from concept to production. Every peak is at the end of each phase when the test and validation take place. The setback is due to not analyzing the vehicle system globally for various attributes, while the design, CAD, CAE, and manufacturing are done in a separate environment. The green curve represents the ACP process when design, CAD, CAE, and manufacturing are synchronized under multidisciplinary load cases. Therefore, the maturity of the product continues and provides a 30 to 35% reduction in time to market usage. The ACP process technology has been implemented in a new software product called ACP OpDesign, a collaboration of ETA Inc. and Beta CAE Systems. For more information, please visit acpopdesign.com, eta.com, or beta-cae.com.
Now we have a good understanding what is ACP process is. Basically, ACP OpDesign is designed based on this process. Let's talk about ACP OpDesign. What is ACP OpDesign? ACP OpDesign architecture. Basically, ACP OpDesign has three major key modules: ACP concept, ACP low fidelity 3G, as we call it LF3G, and also high fidelity 3G. The product is basically using SPDRM as a database manager, and also using ANSA as a key software to go in and out for all the CAE activities. So as we can see in the center, basically all the different functionalities within the SCP is handling between the SPDRM and Meta and ANSA. However, in the different stage of the concept, design concept, and as well as low fidelity and high fidelity, different type of the software can be interfaced. In the concept level, all the topology optimization solvers, and also, regular different solvers such as LS-DYNA and MSC, Nastran can be interfaced during the process, and also all the parametric model optimization can be interfaced. And with our recent development, Lunar will be interfaced with ACP OpDesign. I'd like to turn the mic to Kambiz, who's going to be talking and introducing you to ODYSSEE and Lunar ROM.
This is an introduction to our platform ODYSSEE, in particular concentrating on Lunar module. The technologies we employ are machine learning, reduced order modeling, and optimization. This allows us to handle multiple applications ranging from direct data recordings to CAE output or even images. It also covers any solver, any partial differential equation, be it crash, CFD, NVH, etc. It can handle linear, nonlinear, static, dynamic, bifurcation, buckling, etc. So it's completely independent of the solver because it only looks into the output of that solver. It is used for various real-time sensitivity analysis, optimization, reliability. By real-time, we mean interactive, not to be confused with system engineering. We have applications in at the top left, you have applications in tooling and machining and fault detection. Bottom left, the direct data recordings of Ariane 5. We have applications in the middle top for healthcare, a lot of biomedical, biomechanic applications, bottom, middle, consumer products, any arbitrary consumer product, top right, civil engineering, and bottom right, automotive and engineering, and crash engineering. So what is our technology based on? Well, the idea is to exploit, this is more or less around Lunar, idea is to explore all new machine learning techniques in combination to CAE. So instead of opposing these together, we are now, we think that there's a new solution, technology tool, which is coming out, which is a combination of both. These allow us to provide predictive models which are run much faster, which are very efficient, knowing that simulation has traditionally provided a lot of data, but we have not always exploited these data to our benefit. So this is what we want to do. We want also to connect these CAE-based data to direct control or sensor recordings, allowing us to have a sort of multi-source, or what they call these days digital twin or whatever, solution which allows us to somehow handle much more realistic problems, especially because they are more and more multi-physics related in real time. In the right, you see what we traditionally do in the middle blue square. We go from CAD to modeling and solver. So our intention is to remove the middle block as much as possible and go directly to system parameters, to system responses, including also sensor. Why do we want to do this? Why Lunar? And where is it really efficient? Well, any parametric study or trial and error study which requires in the order of tens of runs is a good candidate. You can remove that CPU costly evaluation of the function by a great factor. If you go to optimization, where we are talking in terms of hundreds of runs, so this function will be more and more costly. And also traditional surrogate models don't really deliver full response or any. I would say it's not sufficient. Here we are very efficient, and of course, when you go to reliability, robustness, you go into thousands of runs, and then the benefit is obvious. Now, this reduced order modeling or fusion is essentially based on decomposition techniques, decomposing a system into spatial or temporal components. Now, if I want to compare ROM method to traditional finite element model, where it's partial differential equation driven, we start by defining the PDE, we discretize it, we provide the input, and we obtain the results. We call this spatial or temporal integration. Now, anything which is ROM-based is data-driven, and it does exactly the inverse by recovering old knowledge or cases, old responses, and going up, trying to understand how that has been created, and we call this learning. If I want to compare this to traditional regression or PCA, etc., so it's very much similar, where everything is data-based, data-driven. You have the blue points and not the red line, which actually define the system. You can also compare the decomposition technique to what we do in modal analysis, where actually the system is decomposed into simpler systems, very much like what we do in fusion technology. And then you solve it, and then you go back. The advantages of this technique, ROM, is that we start from existing models. We don't go and create new stuff. We just use a given model, do a DOE design of experiments around it, and some particular conditions on that DOE are respected. But essentially, this allows us to have, let's say, for the design space, the picture you see on the bottom left, those blue lines, which somehow sample the design space, allow you to have these blue curves, which are some outputs of the system, and then those analyzed and sent into the ROM allow you to have the response for the red points, where the learning is just done once, so you don't do that learning every time. And this is very, very efficient. Allows for real-time computing. That means interactive design. It needs very few sampling points, contrary to response surface methods or surrogate methods, where it's the response surface which imposes its requirements on the DOE. Here, it's not the case. It's the inverse. It's the physical system, and to some extent, we can say it's eigenmodes which define the number of runs needed, and those eigenmodes are bounded, so they are few. It allows us to have full response of the system, full time history, everything which the system has, and not just what the response surface allows us to do, not a few scalars, but you get the full response. It can do animations, it can do stress fields, whatever you had with your solver, you get it back. And most importantly, we also have the possibility to compress data. All the fusion technology is a compression technique, so we can get onboard solvers. These are real-time solvers, let's say, of your crash or your CFD. They can be used in real time, and they can be used for any digital twin application. So I will stop here and probably come back if there are any questions. So I hand over to Akbar again. Thank you very much.
Thanks, Kambiz. So now I'm going to just get into the meat of this project. We're going to talk about OpDesign challenges and our strategy in this project. So within the ACP OpDesign, we have found out there is a little bit of challenges in front of us. Obviously, the timing to do the parametric optimization, especially with the 3G optimization, takes time. And we are looking for how we can reduce that time, which is going to affect the reduction of the time of the product design development and time to market. Also, how could we find several quick, feasible design within the available design variables? And also, how can we use ACP OpDesign quickly in the case that HPC computing is not available? So to answer with these challenges, we come up with a strategy that if we showed how we can use AI ML within the Lunar package and its effectiveness and reducing the time, we can easily scale up this one case into the several cases and in the multidisciplinary optimization cases. Therefore, this could be definitely an effective solution. The case study for this project is working on the future steel vehicle, and we're going to show how effective we can apply this technology for frontal crash on this project. In this slide, I'm showing an overview of the project that we did for World Auto Steel and the effectiveness of the ACP process, how we started from the blobs, creating the skeleton, and from the skeleton, we drive that based on the load path that we had, generate the 3D geometry using our technology and softwares that we use within the ANSA, and developing the low fidelity model, which we then apply the 3G optimization, which is geometry, gauge, and grade, and gauges, and reduce the mass in certain percentage. And then we went to the high fidelity and looked into the different components and designed it in the detail and look at the manufacturing processes and looking at how we can reduce the weight as well as increasing the performance. This whole process, we reduced the weight by 39% while we are meeting all the requirements. For our study and our purpose, we are just going to take the high fidelity design, one of the high fidelity design, and perform the frontal crash on that and see how we can reduce the parametric optimization timing that took us 150 or 200 runs to be reduced by Lunar. Let's talk about the CAE model that we use for this study, which is the frontal crash model with about 500,000 elements, about 1,000 kilogram mass, and the simulation time using 48 core HPC was taken about 1 hour. So we can estimate if we say, we are using 150 runs, how long will it take? And this simulation is just for the FMVSS 208 front crash rigid wall impact. Here we are looking at this baseline optimization that we are going to perform with Lunar. We have a pulse of 54 Gs in about 40 to 50 millisecond, which is pretty high. We picked up just the one run of the through the optimization process. Intentionally, we picked up the one of the runs that we get a very high pulse, so we can see what Lunar can do with that, and the target of the 120 millimeters dash intrusion. And our target was basically 35 Gs, which is hopefully, that gives us like 5-star within the 40 to 60 millisecond. In this slide, we show the frontal crash model, the components that are absorbing energy and passing the load. Those are the key components that we are putting design variable. We parameterize them and we allow them to change the geometry and the gauge and the grade. We came up with about 15 design variables for the thicknesses and other designs for the geometry. On the traditional DOE direct optimization, we had about 150 design iteration. Now we want to see, how effective is IML solution and how effective and how we can reduce the number of the DOE size of optimization. Okay, so let's look at this high fidelity 3G optimization using Lunar. Based on our study, we have 3 major steps to take. In step 1, to generate DOE inputs, we basically take the number of the design variables that we have, and we have a kind of rules of the 2N, started with the 2N as a starting point for the number of the runs that we are going to get from LS-DYNA. So we had about 30 runs with LS-DYNA with the responses, as you can see in the bottom right. Those are the responses, and we have also a scattered picture of the different runs that is showing in the left and the bottom of the slide. And so basically ML algorithm learns from these 30 runs or 30 plus if you want it, to predict the responses for the prediction of the best design that it can meet our targets. This step, we call it validation. Before we do any optimization, we want to make sure whatever DOE analysis that we have, responses that we have as a feeding and the learning for Lunar is good enough, and how we can predict the responses. So as we can see, with the number of design variables and number of runs, which was about 30 runs, it's pretty good. Lunar has predicted very good the peak pulse. They're very much in agreement. Obviously, we can get much closer than this, but we thought this is good enough. And let's see, what we can do next step when we fit this into the Lunar and do the actual optimization. In step 3, optimization using Lunar, we basically fit all this information with the validation that we had, and selecting different type of the optimization algorithm. We can just, and using our objective and constraint, we can run the optimization and see how good we do that. And basically, we had a 30G targets. And as we can see, Lunar was able to predict or very well, and also optimize it based on the 35 Gs. And we are achieving that, results very, very, very quickly and efficiently, as we can see in the comparison curve that we have. The magenta is CAE confirmation, and Lunar is the green. As you will see in the next slide, we meet all the other requirements as well. In this slide, we have a comparison of the traditional optimization method, which we did it with LSOP, but it can be done by any commercial software, and against Lunar, and see how Lunar does with both animations and actual numbers. And as we can see, the prediction and also the optimized results is very good, is excellent. The animations shows very well, coincide with the CAE results. And on the pulse, as we can see, the peak pulse from the let's say 50 some Gs, 54 Gs, from the one single peak has been distributed to two hump on the blue curve on the pulses, which is very, very nice. That way, is distributing the whole energy within the design space. And we are meeting 35 Gs, which is excellent. And as well, if you look at the topan intrusion, because once we bring the pulse down, your intrusion could go up. However, our intrusion throughout the whole system and the dash is pretty consistent and very well within the design target. And this is an excellent result. The comparison of running 150 runs against 30 runs and a minute of doing the optimization, or less than a minute of the Lunar optimization. Okay, the summary and the conclusion of this work, as we indicated, was reduction of the both DOE sizes for the initial prediction, and also reducing the CPU time dramatically, about 80% for both from DOE sizes and as well as CPU time. That's a huge help for us when we are using ACP OpDesign on the full vehicle under multidisciplinary load cases, let's say about 6, 7, 8 crash load cases, plus durability and stiffness and NVH load cases. That is going to be a very, very helpful to reduce the number of the parametric optimization, which is very important in our process. And we think with this interface with Lunar, we are going to be aggressively going after reducing the product time reduction and product design development time reduction, and reducing the CAE time simulation for a number of the iterations, whether we are going to use ACP OpDesign or outside of this process. So with that, I'd like to thank you for your attention. I'd like to thank my partners and co-authors, and Dr. Kambiz Kevantash for his help and assistance to do this project together. Thank you very much, and we look forward to see your questions.